Hello, and welcome to Somniora Mind. I'm glad you're here. I want to start tonight with a question that sounds simple but isn't. What is between the galaxies? Most people, if they think about it at all, imagine emptiness. A pure, featureless void. Nothing. The kind of nothing that doesn't need to be described because there's nothing there to describe. But that answer is wrong. Completely, fascinatingly, almost insultingly wrong. The space between galaxies is not nothing. It is one of the most complex, dynamic, and strange environments in the known universe, filled with invisible matter, ancient light, high-energy particles, magnetic fields, rivers of gas, the shock waves of collisions that happened billions of years ago, and a web of structures so enormous that individual galaxies are just the bright nodes where the threads cross. Tonight we are going there, not to the galaxies themselves, but to the space between them, to the medium that connects them, the forces that shape them, and the architecture that underlies everything we can see. We are going to the most underappreciated part of the cosmos, the vast, strange, magnificent nothing that is not nothing at all. Before we begin, if Somniora Mind gives your mind a quiet place to land at the end of the day, please consider subscribing. You're already the kind of person this channel was made for, one quiet mind at a time. I want to plant 3 ideas in your mind before we start, and we'll return to all of them before tonight is done. First, the space between galaxies contains more ordinary matter than all the galaxies combined. It's just hidden in a form we can barely detect. Second, the structure of intergalactic space was drawn by a force we have never seen and cannot directly measure. And third, somewhere out there, beyond the edge of our galaxy, stars are drifting alone in the dark between galaxies, with no galaxy to call home. We'll get to all of it. Let's go. The space between galaxies is not a vacuum in any ordinary sense. The word vacuum suggests absence, a container with nothing inside. But intergalactic space is permeated by matter, radiation, magnetic fields, and energy in various forms, all of which interact with each other and with the galaxies they surround. The intergalactic medium, the diffuse material that fills the spaces between galaxies, is extraordinarily thin by any laboratory standard. In some regions, there is less than 1 atom per cubic meter, compared to the roughly 10 to the power of 25 atoms per cubic meter in the air you are breathing. But this near emptiness extends over distances so vast that its total mass is enormous. The intergalactic medium is thought to contain a significant fraction of all the ordinary matter in the universe, scattered across the largest volumes of space that exist. What appears, from a distance, to be darkness and void is, in fact, a universe-spanning ocean of almost unimaginably thin gas. The cosmic web is the largest known structure in the universe. At the very largest scales, the matter in the universe is not distributed randomly or uniformly. It is organized into a vast network of filaments, sheets, and nodes separated by enormous empty regions, a structure astronomers call the cosmic web. The filaments are the threads, long, curved rivers of dark matter and gas that stretch for tens to hundreds of millions of light years. Where filaments intersect, matter accumulates into galaxy clusters, the densest, most massive gravitationally bound structures in the universe. Between the filaments lie the voids, regions largely devoid of bright galaxies, spanning hundreds of millions of light years in diameter. The cosmic web is not a metaphor. It is a real, measured, three-dimensional structure, mapped through the positions of millions of galaxies across the observable universe. It is the skeleton of the cosmos, the underlying architecture that determines where galaxies exist and where they do not. The cosmic web was predicted before it was observed. In the late 1970s and early 1980s, cosmologists using early computer simulations of structure formation predicted that the matter in the universe should, over billions of years, organize itself into a network of filaments and voids driven by the gravity of dark matter. When the first large-scale galaxy surveys began mapping the three-dimensional distribution of galaxies in the universe, the predictions were confirmed with striking fidelity. The galaxy maps showed exactly the filamentary, void-dominated structure that the simulations had predicted. The agreement between theory and observation was one of the most important validations of the dark matter model and of the overall framework of cosmological structure formation. The cosmic web was written into the equations before anyone had seen it, predicted from first principles, and then found exactly where the mathematics said it would be. Cosmic voids are the largest structures in the universe by volume. Between the filaments and galaxy clusters of the cosmic web lie the voids, enormous regions containing very few galaxies and very little matter of any kind. The largest known voids span hundreds of millions of light-years. The Boötes void, one of the most famous, stretches approximately 330 million light-years across and contains far fewer galaxies than the surrounding regions of the universe. If you were to place our entire Milky Way galaxy at the center of the Boötes void, the nearest large galaxy would be hundreds of millions of light-years away, a distance so immense that the light from that neighbor would take hundreds of millions of years to reach you. Voids are not simply empty space. They are regions where the universe has, over billions of years, evacuated matter toward the surrounding filaments and walls, leaving behind an environment that is as close to true emptiness as the universe gets. And even there, the void is not quite empty. Even the voids contain something. Despite their name and reputation, cosmic voids are not completely empty. They contain diffuse gas, hydrogen and helium in their simplest forms, the leftovers of the Big Bang that never made it into stars or galaxies. They contain isolated dwarf galaxies, small, faint systems that formed from the minimal material that remained in void regions after the major evacuation of matter toward filaments. They contain dark matter in lower concentrations than the surrounding filaments, and they are permeated by radiation, photons from the cosmic microwave background, ultraviolet light from distant quasars, and the diffuse X-ray background. A void is not an absence, but a different kind of presence. A region where the universe's average density is substantially below the cosmic mean, where the dominant feeling, if you could be there, would not be total emptiness, but an extraordinary, almost unimaginable sparseness. The filaments of the cosmic web contain rivers of gas flowing toward galaxy clusters. The filaments that make up the cosmic web are not static structures. They are dynamic channels through which gas flows, under the influence of gravity, toward the galaxy clusters that sit at their intersections. This cosmic accretion, the slow infall of intergalactic gas along filaments and into clusters, is one of the primary ways in which galaxies receive the fresh material they need to form new stars. Without this supply of gas from the cosmic web, the star-forming regions of galaxies would exhaust their fuel far more quickly than observed. The filaments are, in this sense, the feeding tubes of the universe, slow, enormous rivers of gas that connect the diffuse intergalactic medium to the dense cores of clusters, sustaining the cycle of matter and star formation that has been running since the first galaxies ignited. The warm-hot intergalactic medium holds a significant fraction of all ordinary matter. For decades, astronomers cataloging the matter in the universe found that the amount of ordinary baryonic matter they could account for in stars, galaxies, gas clouds, and hot cluster gas fell significantly short of the amount predicted by cosmological models. This was called the missing baryon problem. The solution, now increasingly well supported by observations, is that the missing matter is not truly missing but is hidden in a diffuse, warm hot gas that fills the filaments of the cosmic web. Temperatures ranging from 100,000 to 10 million degrees Celsius, too cool to emit strongly in X-rays, but too hot to be detected in visible light. This warm-hot intergalactic medium, or WIM, is extremely difficult to observe, but has been detected in ultraviolet and soft X-ray observations along lines of sight to distant quasars. It may account for nearly half of all the ordinary matter in the universe, a vast, nearly invisible ocean of hot gas threading through the spaces between galaxies. The intergalactic medium was reionized by the first stars and galaxies. In the earliest epochs of the universe, after the cosmic dark ages when no stars yet existed, the hydrogen gas that filled the universe was in a neutral state, atoms with their electrons attached. When the first stars and galaxies ignited, the ultraviolet radiation they produced was powerful enough to strip electrons from hydrogen atoms in the surrounding gas, converting it from neutral hydrogen to ionized plasma. This process, called reionization, gradually spread outward from the first luminous sources, like bubbles of ionized gas expanding into neutral fog, until the bubbles overlapped and the entire universe was reionized, a transition that took several 100 million years and was completed roughly 1 billion years after the Big Bang. The intergalactic medium we observe today, largely transparent to visible light and ionized throughout, is the product of this ancient transformation, carried out by sources of radiation that no longer exist in the forms they once took. Quasars illuminate the intergalactic medium like cosmic flashlights. Quasars, the intensely luminous cores of distant active galaxies, powered by supermassive black holes consuming enormous quantities of gas, are among the most useful tools for studying the intergalactic medium. As the light from a distant quasar travels toward us through billions of light years of intergalactic space, it passes through the diffuse gas that fills that space. Different elements in the gas absorb the quasar's light at specific wavelengths, leaving characteristic dips in the spectrum that reveal what the gas between us and the quasar contains. This technique, quasar absorption spectroscopy, has revealed the temperature, density, and chemical composition of the intergalactic medium across billions of years of cosmic history. A quasar is not merely an object to be studied in its own right. It is a backlight, a brilliant, distant source whose light, on its way to our telescopes, carries the imprint of everything it has passed through. The Lyman alpha forest encodes the history of intergalactic hydrogen. In the spectra of distant quasars, there is a distinctive feature called the Lyman alpha forest, a dense thicket of absorption lines produced by hydrogen atoms in the intergalactic medium at different distances along the line of sight. Each line in the forest represents a discrete cloud of hydrogen gas absorbing light at the specific wavelength associated with the Lyman alpha transition of hydrogen, but redshifted by the expansion of the universe to longer wavelengths that depend on the distance of the absorbing gas. A forest of hundreds of absorption lines in a single quasar spectrum therefore encodes the distribution of hydrogen gas across billions of light years of cosmic history, with each line marking a different epoch and a different location along the line of sight. The Lyman alpha forest has been used to study the large-scale structure of the universe, the thermal history of the intergalactic medium, and the properties of dark matter on small scales, all from the spectrum of a single distant quasar. The local group is the Milky Way's immediate intergalactic neighborhood. The Milky Way does not exist in isolation. It is a member of a gravitationally bound collection of galaxies called the local group. a system containing more than 50 galaxies of various sizes, spanning roughly 10 million light-years. The two dominant members are the Milky Way and the Andromeda Galaxy, each surrounded by their own collections of satellite dwarf galaxies. The smaller members of the local group include the Magellanic Clouds, visible from the southern hemisphere as bright patches of the Milky Way, and dozens of faint dwarf galaxies scattered across the volume of the group. The intergalactic space within the local group, the space between the Milky Way, Andromeda, and their satellites, is itself a region of gas, dark matter, and gravitational dynamics, not empty in any meaningful sense, but a shared gravitational environment in which all the member galaxies are embedded and through which they move. Andromeda and the Milky Way are connected by a bridge of stars and gas. The space between the Milky Way and the Andromeda Galaxy is not entirely empty of matter. Observations have revealed streams of stars and gas stretching between the two galaxies and their satellites, material drawn out by gravitational interactions over billions of years. The Magellanic Stream, a ribbon of hydrogen gas extending from the large and small Magellanic Clouds across hundreds of thousands of light-years of the southern sky, is one of the most prominent examples, a bridge of intergalactic gas connecting satellite galaxies to the Milky Way's halo. Similar bridges and streams connect other members of the local group, creating a network of tenuous material linking what would otherwise appear to be isolated islands of stars. The intergalactic space within a galaxy group is, in this sense, not a separation but a connective tissue, thin, barely visible, but real. Galaxy clusters are the most massive gravitationally bound structures in the universe. At the densest nodes of the cosmic web sit galaxy clusters, enormous structures containing hundreds to thousands of galaxies, along with vast reservoirs of hot gas and enormous quantities of dark matter. The total mass of a rich galaxy cluster can reach 10 to the power of 15 solar masses, a quadrillion times the mass of the Sun, making them the largest gravitationally bound objects in existence. The Coma Cluster, one of the nearest rich clusters to Earth, contains more than 1,000 galaxies within a region about 20 million light-years across, all held together by a common gravitational field. Between the galaxies and the cluster is the intracluster medium, hot gas at temperatures of tens of millions of degrees, glowing in X-rays, with a total mass that exceeds the combined mass of all the visible galaxies in the cluster. The galaxies themselves, dazzling as they are a minority component of the cluster's total mass. Most of it is invisible. The intracluster medium is the hottest large-scale gas in the universe. The gas that fills the space between galaxies within a cluster, the intracluster medium, is heated to temperatures of 10 to 100 million degrees Celsius by the gravitational energy released as matter falls into the cluster's deep gravitational well. At these temperatures, the gas glows not in visible light but in X-rays, making galaxy clusters among the brightest X-ray objects in the sky. The intracluster medium is in a state of continuous dynamic activity. It is heated by jets from supermassive black holes in the cluster's central galaxy, stirred by the passage of infalling galaxies, and compressed by shock waves from cluster mergers. X-ray observations of galaxy clusters have been one of the primary ways astronomers study the properties of dark matter, because the distribution of the hot gas traces the overall gravitational potential of the cluster, which is dominated by the dark matter that cannot be directly observed. Dark matter is the architect of intergalactic structure. Everything in intergalactic space, the cosmic web, the filaments, the voids, the cluster nodes, the way gas flows between them, was shaped primarily not by ordinary matter but by dark matter. a form of mass that interacts with gravity, but not with light or electromagnetism. Dark matter cannot be seen, emitted, absorbed, or detected with any current instrument in any direct way. It is known only through its gravitational effects, the way it bends light, holds galaxies together, and creates the scaffolding on which the cosmic web is built. Dark matter began to clump together early in the universe's history, before ordinary matter had cooled enough to condense. Over billions of years, these dark matter concentrations, called halos, grew by gravitational attraction, merging with each other to form increasingly large structures. The ordinary matter of gas and stars fell into the dark matter halos, lighting them up as galaxies and clusters. What we see when we look at the universe is ordinary matter illuminating the outlines of a dark matter scaffolding we cannot see directly. The Great Attractor is pulling the Milky Way and millions of other galaxies toward it. In the direction of the constellations Centaurus and Norma, something is pulling. Not just the Milky Way, but the local group, the Virgo supercluster, and tens of thousands of other galaxies are all moving at several hundred kilometers per second toward a region of space that lies partially hidden behind the dense band of the Milky Way itself. This region, called the Great Attractor, represents an enormous concentration of mass, including the Hydra Centaurus supercluster and, beyond it, an even larger structure called the Shapley supercluster, one of the most massive concentrations of matter in the observable universe. We are in freefall toward it, carried along by gravity on a journey that will take hundreds of millions of years to play out. The Great Attractor is not a single object. It is a region where the cosmic web has produced an extraordinary accumulation of mass, and which is exerting its gravitational influence across hundreds of millions of light years. Laniakea is the supercluster that contains our galaxy, and it is enormous. In 2014, a team of astronomers led by Brent Tully mapped the flow of galaxies in the local universe and found that more than 100,000 galaxies, including the Milky Way, are all falling toward a common center, tracing out the boundaries of a single enormous supercluster. They named it Laniakea, meaning immeasurable heaven in Hawaiian. Laniakea spans roughly 520 million light-years and contains the mass of 100 million billion suns distributed across its constituent galaxy groups and clusters. The Milky Way is located near the outer edge of Laniakea, far from its central concentration. When you look at a map of Laniakea, the Milky Way appears as one tiny point among thousands, near the periphery of a structure so vast that the light crossing it takes more than 500 million years. We are not at the center of anything. We are near the outskirts of a cosmic suburb, part of an immeasurably large neighborhood. Intergalactic stars drift alone between galaxies. Not all stars belong to galaxies. A significant population of stars, called intergalactic stars or intracluster stars, exists in the spaces between galaxies, particularly within galaxy clusters. These stars were stripped from their home galaxies by tidal forces during the close passages of galaxies through the cluster environment, ejected into the intracluster space, where they now drift without any galactic affiliation. The collective glow of these intergalactic stars forms a diffuse, extremely faint halo of light around galaxy clusters. The intracluster light, that can be detected with sensitive imaging systems as a ghostly luminescence permeating the space between the cluster's galaxies. Individual intergalactic stars cannot be resolved at cluster distances, but in nearby groups they can sometimes be identified one by one. They are the most solitary stars in the universe. Having once been members of galaxies, they now travel through the vast spaces between them, illuminating nothing, orbiting nothing, drifting on trajectories that will carry them through the intergalactic dark for billions of years. Some intergalactic stars may host planets. The intergalactic stars that drift through the spaces between galaxies formed within galaxies, surrounded by protoplanetary disks like any other star. Some of those stars may have formed planets before they were ejected from their home galaxies by tidal forces. If so, there may be planetary systems drifting through intergalactic space, worlds orbiting stars that have no galaxy, in a sky that contains no Milky Way, no nearby star fields, only the faint smudges of distant galaxies scattered across an otherwise dark sky. From the surface of a planet orbiting an intergalactic star, the night sky would be profoundly different from any sky on Earth. The nearest star might be millions of light years away, and the sky would contain not the thousands of stars visible from our own world, but perhaps only the faint glow of distant galaxies, each containing hundreds of billions of stars, but none close enough to appear as more than a softly blurred point of light. It would be the loneliest sky imaginable. Superclusters are not gravitationally bound. They are being pulled apart by dark energy. Galaxy clusters are gravitationally bound. Their member galaxies are tied together by mutual gravity and will remain together for the foreseeable future. But the larger structures, the superclusters and the cosmic web, are not gravitationally bound in the same way. The expansion of the universe, driven by dark energy, is pulling them apart faster than gravity can hold them together. Laniakea, for example, will not survive as a coherent structure. Its outer regions are already being carried away by the expansion, and over billions of years it will gradually disperse as dark energy continues to accelerate the separation of its constituent clusters. The cosmic web, in this sense, is a transient structure. It represents the large-scale organization of matter at this particular epoch in the universe's history, not a permanent feature. In the far future, as dark energy continues to dominate, the cosmic web will gradually dissolve, leaving only the most strongly gravitationally bound structures, galaxy clusters and groups, as isolated islands in an increasingly empty and expanding universe. Galaxy mergers reshape the intergalactic environment. When two galaxies collide and merge, the event is not merely a local rearrangement of stars and gas. It has consequences for the intergalactic environment surrounding the merger. Gas from the merging galaxies can be ejected into the surrounding intergalactic medium, enriching it with heavy elements. The supermassive black holes at the centers of the merging galaxies eventually find each other and spiral together, producing gravitational waves and, in the lead-up to the merger, potentially triggering periods of intense activity in which jets of material are launched outward at near the speed of light. These jets carry energy deep into the intergalactic medium, heating the surrounding gas and influencing the formation of new galaxies. A major galaxy merger is therefore not just a local event, but a driver of change in the surrounding intergalactic environment, a source of energy, matter, and disturbance that propagates outward from the merger site across millions of light years. The Bullet Cluster is the most direct evidence for dark matter ever found. The Bullet Cluster is the aftermath of a collision between two galaxy clusters, observed about 3.8 billion light-years from Earth. When the two clusters collided, the hot gas of each cluster, which constitutes most of the ordinary matter, was slowed and heated by electromagnetic interactions between the gas clouds, while the dark matter, which does not interact electromagnetically, passed through the collision without slowing down. The result is a structure in which the ordinary matter, visible in X-rays as a hot, distorted blob, has separated from the dark matter, which continued forward and is detected through its gravitational lensing of background galaxies. This spatial separation between where ordinary matter is and where the mass must be, as indicated by lensing, is one of the most compelling and direct pieces of evidence that dark matter is a real component of the universe, not simply an artifact of modified gravity theories. The bullet cluster makes the case for dark matter with a clarity that few other observations can match. Gravitational lensing allows us to map the invisible matter in intergalactic space, one of the most powerful tools for studying the distribution of matter in intergalactic space, including the dark matter that dominates the mass budget, is gravitational lensing, the bending of light from distant objects by the gravitational fields of matter lying between those objects and Earth. This is not a lens in the optical sense, but a gravitational deflection of photon paths that produces distortions, arcs, and multiple images of background objects when matter is present along the line of sight. By measuring the shapes and positions of thousands of background galaxies, astronomers can reconstruct the distribution of mass in the foreground, including the dark matter that produces most of the lensing effect. Weak gravitational lensing surveys, in which the average distortion of many faint background galaxies is measured statistically, have produced maps of the large-scale dark matter distribution across large areas of the sky, maps of the invisible scaffolding on which the visible universe is built. Radio galaxies and their jets extend deep into intergalactic space. Some of the most dramatic objects in intergalactic space are the extended radio structures produced by active galactic nuclei, jets of relativistic plasma launched by supermassive black holes that extend outward from their host galaxies for hundreds of thousands or even millions of light years into the surrounding intergalactic medium. These jets carry enormous amounts of energy far from their source galaxies, depositing it into the intergalactic medium and inflating enormous bubbles or lobes of relativistic plasma that glow at radio wavelengths. The largest known radio galaxies have structures extending for tens of millions of light years, among the largest individual structures produced by any physical process in the universe. As these jets propagate through the intergalactic medium, they create shock waves that heat the surrounding gas, and they can disrupt the smooth flow of gas along filaments, altering the environment for galaxy formation in the surrounding region. A jet from a single black hole can influence the intergalactic environment for tens of millions of light years in every direction. The temperature of the intergalactic medium encodes the history of the universe. The intergalactic medium is not at a uniform temperature. In the dense, hot gas of galaxy clusters and the filaments that connect them, temperatures reach tens of millions of degrees. In the diffuse gas of the voids, temperatures are much lower, though still far above what we associate with cold in everyday life, because even the most diffuse intergalactic gas has been heated by radiation from stars and quasars. The thermal history of the intergalactic medium, how it was heated and when, is written in the temperature distribution of the gas we observe today. Reionization, which heated the entire intergalactic medium rapidly as the first galaxies ignited, set the baseline temperature. Subsequent heating from quasar radiation, shock waves from structure formation, and feedback from galaxies has modified this baseline in complex ways. By measuring the temperature of the intergalactic medium at different epochs and in different environments, astronomers reconstruct the history of energy injection into intergalactic space over billions of years. The universe has vast regions where no bright galaxy exists. The largest cosmic voids are not merely regions of below-average galaxy density. They are regions where bright, massive galaxies are almost completely absent over volumes spanning hundreds of millions of light years. The KBC void, identified in 2013, is a region of below-average density centered roughly on the local group and extending for about 1 billion light-years, making it the largest known underdensity in the local universe. Whether such large voids are consistent with standard cosmological models or represent a challenge to them is an active area of research. What is clear is that the universe contains, on its largest scales, a genuine patchwork of rich and poor regions, dense filaments and clusters, and vast expanses where the cosmic web has drawn matter away and left an environment that is, by the standards of the universe, astonishingly empty. Magnetic fields thread through intergalactic space. The intergalactic medium is not only permeated by gas and radiation, it also contains magnetic fields extending over cosmological scales. These intergalactic magnetic fields are extremely weak, estimated to be 1 billion to 1 quadrillion times weaker than Earth's magnetic field, but they extend over distances of millions of light years. Their origin is uncertain. They may have been produced in the early universe during phase transitions or other energetic events, amplified by the dynamo action of galaxies and jets, or generated during the process of structure formation. Whatever their origin, intergalactic magnetic fields influence the propagation of cosmic rays through the universe, affect the thermal state of the intergalactic medium, and can be amplified in galaxy clusters to strengths measurable by radio observations. Mapping the intergalactic magnetic field, understanding its spatial structure, its strength, and its evolution, is one of the frontiers of observational cosmology. Cosmic rays from beyond our galaxy reach Earth continuously. The highest energy cosmic rays, particles, mostly protons and atomic nuclei, that arrive at Earth with energies far exceeding anything achievable in the most powerful human-built accelerators, are thought to originate from sources outside the Milky Way, from active galactic nuclei, gamma-ray bursts, or other powerful extragalactic sources. These particles travel through intergalactic space, deflected and scattered by intergalactic magnetic fields, losing energy through interactions with photons of the cosmic microwave background. The most energetic known cosmic rays have energies so extreme that interactions with background photons limit their travel distance. They can only reach Earth if their sources are within a few 100 million light-years. Identifying the specific sources of ultra-high-energy cosmic rays is one of the outstanding problems of high-energy astrophysics, requiring the detection of particles that arrive one at a time in enormous ground-based detector arrays, each carrying the kinetic energy of a fast-pitched baseball concentrated into a single subatomic particle. The Sunyaev-Zel'dovich effect reveals galaxy clusters through the cosmic microwave background. When the photons of the cosmic microwave background, the ancient light produced 380,000 years after the Big Bang, pass through the hot gas of a galaxy cluster on their way to our detectors, they gain a small amount of energy through inverse Compton scattering. Electrons in the hot cluster gas boost the energy of CMB photons, shifting them to slightly higher frequencies. This effect, the Sunyaev-Zel'dovich effect, produces a characteristic distortion in the spectrum of the CMB in the direction of the cluster, a slight deficit of photons at low frequencies and a slight excess at high frequencies. This distortion is proportional to the pressure of the cluster gas integrated along the line of sight, making it a sensitive probe of the mass and thermodynamic state of galaxy clusters. Crucially, the Sunyaev-Zel'dovich effect does not diminish with distance the way ordinary brightness does. A cluster at redshift 10 would produce the same signal strength as one at redshift 1 if it had the same mass. This makes the effect a uniquely powerful tool for finding and characterizing galaxy clusters across the entire observable universe. Intergalactic gas has been enriched by metals expelled from galaxies. The intergalactic medium is not composed of only the primordial hydrogen and helium that emerged from Big Bang nucleosynthesis. It has been progressively enriched with heavier elements: carbon, oxygen, silicon, iron, expelled from galaxies by supernovae, stellar winds, and the energetic outflows driven by supermassive black holes. These heavy elements travel outward from galaxies in galactic winds, sometimes reaching speeds of thousands of kilometers per second, and can be transported over distances of millions of light years from their source galaxies. The detection of carbon and oxygen absorption lines in the spectra of background quasars demonstrates that the intergalactic medium contains measurable quantities of elements that did not exist until stars began fusing them and distributing them through the death and outflow processes of stellar evolution. The intergalactic medium is not the pristine, primordial gas it once was. It carries the chemical legacy of billions of years of stellar birth and death, distributed across the spaces between galaxies by the collective output of every star that has ever lived and died. The first structures in the intergalactic medium were filaments, not galaxies. Before galaxies existed, in the first few 100 million years after the Big Bang, the universe was not empty between the first condensing objects, but filled with neutral hydrogen gas organized by the gravity of dark matter into sheets, filaments, and halos that would eventually become the scaffold for galaxy formation. The first stars and proto-galaxies formed not randomly, but at the denser intersections of this early dark matter web. The intergalactic structure preceded the galaxies that would eventually illuminate it. In a real sense, the cosmic web was not built by galaxies. It was the condition that made galaxies possible. The galaxies formed inside the web, at its densest points, fed by the gas flowing along its filaments, shaped by the gravity of its dark matter halos. The structure came first. The light followed. The expansion of the universe is stretching intergalactic space. The space between galaxies, and indeed between everything, is continuously expanding. This is not a motion of galaxies through space, but an expansion of space itself. The distances between objects not bound by gravity are growing, as they have been since the Big Bang. On scales smaller than galaxy clusters, gravity is strong enough to hold structures together against the expansion. On larger scales, the expansion wins. The distances between clusters and superclusters are growing. The expansion is accelerating, driven by dark energy, the unknown form of energy that permeates all of space and acts as a repulsive force on the largest scales. As the expansion accelerates, intergalactic distances grow faster and faster. Galaxies that are currently receding from us will eventually be carried beyond our cosmic horizon, the point from which their light can never reach us, and will disappear from the observable universe forever. The intergalactic space is not a fixed stage on which cosmic events play out. It is itself the subject of the most consequential physical process in the universe. Tidal streams in intergalactic space are the remnants of destroyed galaxies. When a smaller galaxy passes too close to a larger one, the gravitational tidal forces of the larger system can tear the smaller one apart, drawing its stars out into a long, curving stream that wraps around the larger galaxy. These tidal streams, also called stellar streams in cases where the disrupted object is a globular cluster, trace the orbits of their progenitor objects over many billions of years. They are among the most delicate and beautiful structures in the universe. Gossamer threads of stars stretched across hundreds of thousands of light years, gradually dispersing over billions of years until they are indistinguishable from the diffuse stellar halo. Around the Milky Way, more than a dozen stellar streams have been identified, each the remnant of a smaller galaxy or cluster that was disrupted on its way into the Milky Way's gravitational embrace. Around other galaxies, seen from outside, these tidal streams appear as arcs and ribbons of faint starlight in the otherwise dark intergalactic space surrounding the galaxy, the signatures of consumed companions. Galaxy groups are the most common galaxy environment. While galaxy clusters receive the most attention because their size and luminosity make them the most dramatic objects in the universe, the most common environment for galaxies is not the rich cluster, but the modest galaxy group, a collection of a few to a few dozen galaxies bound together by gravity in a region a few million light-years across. The local group, which contains the Milky Way, Andromeda, and their satellites, is a typical galaxy group in many respects. The intergalactic space within a galaxy group, the space between the member galaxies, contains hot gas at lower temperatures and lower densities than cluster gas, tidal streams of stars from past interactions, and dark matter halos that partially overlap. Most galaxies in the universe have spent their entire histories within groups, their evolution shaped by the interactions, minor mergers, and shared gas environment of the group rather than the more extreme conditions of the richest clusters. The mass of intergalactic gas in clusters exceeds the mass of their stars. When we look at a galaxy cluster in visible light, we see the bright points of its member galaxies, each containing hundreds of billions of stars. These galaxies are luminous and visually dominant, but they are not where most of the ordinary matter in the cluster resides. The hot intracluster gas, detected in X-rays, typically contains 5 to 10 times the mass of all the stars in the cluster's galaxies combined. The stars we see, magnificent as they are, represent only a small fraction of the cluster's ordinary matter content. And the ordinary matter itself, gas plus stars, represents only about 15 to 20% of the cluster's total mass. The rest is dark matter, invisible, unlit, known only through its gravitational effects on the gas, the stars, and the light from background objects. A galaxy cluster is, by mass, overwhelmingly composed of things that cannot be seen. The intergalactic medium absorbs and re-emits radiation continuously. The gas that fills intergalactic space is not a passive medium through which radiation simply travels unimpeded. It interacts with radiation in complex ways, absorbing ultraviolet photons and re-emitting them at different wavelengths, scattering X-rays, allowing some wavelengths to pass freely while being opaque to others. The Lyman alpha photons from distant quasars are absorbed by neutral hydrogen along the line of sight and re-emitted in random directions, creating the Lyman alpha forest described earlier. X-rays from distant sources are scattered and absorbed by the warm-hot intergalactic medium. Radio waves are affected by intergalactic magnetic fields. Even the cosmic microwave background photons are slightly altered in their passage through galaxy clusters by the Sunyaev-Zeldovich effect. The intergalactic medium is not a window through which we observe the universe. It is a participant in the light's journey, altering its spectrum and intensity in ways that encode information about the medium itself. The fate of intergalactic gas determines whether galaxies live or die. The cycle of gas between the intergalactic medium, galaxies, and back into the intergalactic medium through winds and jets is one of the primary regulators of galaxy evolution. A galaxy that receives a steady supply of cool intergalactic gas along cosmic web filaments can continue forming stars indefinitely. A galaxy that is stripped of its gas supply, either because it has entered the hot environment of a cluster or because feedback from its central black hole has heated the surrounding medium, will gradually exhaust its star-forming fuel and transition from a blue, actively star-forming system to a red, quiescent one. This process, called quenching, is thought to be one of the primary drivers of galaxy evolution over cosmic time. The intergalactic medium is not merely the space between galaxies. It is the reservoir from which galaxies draw sustenance and into which they exhale the products of stellar evolution. The relationship between a galaxy and its intergalactic environment is symbiotic, continuous, and ultimately decisive for the galaxy's fate. Some galaxies are being ram pressure stripped as they fall through the intergalactic medium. When a galaxy moves rapidly through the hot gas of a galaxy cluster, the intracluster medium acts like a headwind, exerting pressure on the galaxy's own gas. If the galaxy is moving fast enough and the cluster gas is dense enough, this ram pressure can strip the gas from the galaxy's disk as effectively as wind stripping leaves from a tree. The stripped gas is left behind the galaxy as a long tail, jellyfish galaxies, as astronomers call them, whose gas trails bear an uncanny resemblance to the tentacles of the animal. These tails can extend for hundreds of thousands of light years behind the galaxy and often contain newly formed stars, born in the stripped gas as it is compressed by the passage through the cluster medium. Ram pressure stripping is one of the most visually dramatic processes in the universe and one of the most important mechanisms by which the cluster environment quenches star formation in infalling galaxies. Cosmic filaments rotate. In 2021, astronomers reported evidence that the cosmic filaments of the large-scale structure are not merely passive conduits for matter flowing toward galaxy clusters, but that they rotate, spinning slowly around their own axes on scales of hundreds of millions of light years. The rotation was inferred from the systematic pattern in the velocities of galaxies along filaments, which showed a net rotational component consistent with angular momentum acquired during the formation of the filament through the gravitational collapse of matter with a slight initial angular momentum. This was the first observational evidence that the largest structures in the universe rotate, connecting the angular momentum of the cosmic web to the angular momentum of the individual galaxies within it. The discovery suggests that the spin of galaxies, including our own Milky Way, may be inherited from the rotation of the much larger filament in which the galaxy formed, threading a connection between the spin of a single galaxy and the rotation of a structure hundreds of millions of light years long. The speed of light limits what we can know about intergalactic space. Because light travels at a finite speed, approximately 300,000 kilometers per second, every observation of intergalactic space is also an observation of the past. When we detect the light from a galaxy cluster a billion light years away, we are seeing that cluster as it was a billion years ago, when the light now reaching our detectors first left its source. The most distant regions of the intergalactic medium that we can observe are the most ancient. The farthest quasars visible to current telescopes existed when the universe was less than a billion years old. Their intergalactic environments look nothing like the intergalactic space we find ourselves in today. Studying the evolution of the intergalactic medium across cosmic time is therefore an observational act of historical reconstruction, assembling snapshots of the same medium at different epochs into a narrative of change and development that spans the entire history of the universe. The intergalactic medium was simulated before it was fully observed. The large-scale simulations of cosmic structure formation, projects like the Millennium Simulation, Illustris TNG, and the Eagle Project, have produced virtual universes that reproduce the large-scale distribution of galaxies with remarkable fidelity. These simulations follow the evolution of dark matter, gas, stars, and black holes from early in the universe's history to the present, capturing the formation of the cosmic web, the growth of galaxy clusters, the evolution of individual galaxies, and the properties of the intergalactic medium. They predict properties of the intergalactic medium, its temperature distribution, its metal content, the spatial distribution of filaments and voids that can then be tested against observations. The agreement between simulations and observations, where it exists, is evidence that our understanding of the physics of the intergalactic medium is broadly correct. Where disagreements persist, they highlight gaps in our understanding that drive new theoretical and observational efforts. Fast radio bursts probe the intergalactic medium with extraordinary precision. Fast radio bursts, brief, extraordinarily energetic pulses of radio waves that last only milliseconds but release as much energy as the sun emits in days or weeks, are among the most puzzling and potentially most useful phenomena in modern astronomy. Most are thought to originate at cosmological distances billions of light years away. As a fast radio burst travels through the intergalactic medium on its way to Earth, the radio waves at different frequencies are slowed by slightly different amounts by the free electrons in the medium, a phenomenon called dispersion. By measuring the dispersion, the delay between the arrival of high-frequency and low-frequency components of the burst, astronomers can estimate how much electron-containing plasma the burst has passed through. Since the electron content of the intergalactic medium is related to its total gas content, fast radio bursts provide a new and powerful way to probe the density of the intergalactic medium across cosmological distances, and they have already been used to locate some of the universe's missing baryons in the warm-hot intergalactic medium. The distribution of galaxies on the largest scales is fractal-like. The cosmic web has a self-similar character on a range of scales. Clusters contain galaxies, superclusters contain clusters, and larger structures contain superclusters, with voids nested within voids and filaments within filaments. This hierarchical, approximately fractal organization of matter on large scales arises naturally from the gravitational amplification of small initial density fluctuations. The same physical process produces structure on all scales simultaneously, with the characteristic shape of the cosmic web repeated at progressively larger sizes. This self-similarity is not perfect, and the universe does have a characteristic scale beyond which it becomes statistically homogeneous and isotropic, looking the same in all directions and from all locations, as required by the cosmological principle. But within the range of scales spanned by the cosmic web, the hierarchical, nested structure of clusters within superclusters within larger flows gives the large-scale structure of the universe a character that is simultaneously organized and complex, simple in its underlying physics, and bewildering in the richness of what that physics produces. Some galaxy clusters are merging right now. Galaxy cluster mergers are the most energetic events in the universe since the Big Bang, releasing energies of 10 to the power of 64 ergs over timescales of billions of years. When two massive clusters collide, their hot gas clouds interact, creating shock waves that heat the gas further and produce bow shocks visible in X-ray observations. The dark matter halos pass through each other without direct interaction, while the gas is slowed by ram pressure. The merging clusters generate turbulence and bulk motions in the intracluster medium that persist for billions of years after the merger. Radio observations revealed diffuse radio emission, called radio halos and radio relics, produced by cosmic ray electrons accelerated in the turbulence and shock waves of the merger. These structures, extending for millions of light years, are direct evidence of the violence of cluster mergers and of the extraordinary energies involved in the largest collision events in the post-Big Bang universe. Galaxy clusters act as natural gravitational telescopes. Because the enormous mass of a galaxy cluster bends the paths of light rays passing near it, gravitational lensing, a cluster acts as a natural lens that can magnify and distort the images of background galaxies far more distant than the cluster itself. When a background galaxy is closely aligned with a foreground cluster, its light is bent into arcs, rings, or multiple images by the cluster's gravitational field. This lensing effect can magnify the background galaxy by factors of 10 to 100 or more, allowing astronomers to study objects that would otherwise be too faint to detect. The Hubble Space Telescope's Frontier Fields program deliberately targeted 6 massive galaxy clusters specifically to use their gravitational lensing power to observe the most distant and faintest galaxies visible with current technology. This technique has enabled observations of galaxies from the first few hundred million years of the universe, the most distant and ancient galaxies ever studied in detail, using a natural telescope that no human technology could replicate. The cosmic microwave background carries the imprint of the large-scale structure. The cosmic microwave background, the oldest light in the universe, released 380,000 years after the Big Bang, carries subtle imprints of the large-scale structure that has formed since it was emitted. As CMB photons travel through the universe on their way to our detectors, they pass through the gravitational potential wells of galaxy clusters and the large-scale structure of the cosmic web. Photons that pass through a potential well gain energy on the way in and lose it on the way out. But if the well is growing as the photon passes through it, which happens in a universe dominated by dark energy, the photon loses slightly more energy than it gained, producing a slight cold spot in the CMB. This effect, the integrated Sachs-Wolf effect, is a direct signature of dark energy's influence on the large-scale structure, detected by correlating the large-scale CMB temperature map with the distribution of galaxies in the nearby universe. The CMB is not merely a relic of the early universe. It is a continuously updated record of every large-scale structure the photons have passed through on their billion-year journey. Intergalactic space is the largest reservoir of baryons in the universe. Ordinary matter, the protons, neutrons, and electrons that make up everything we can see and touch, is called baryonic matter in cosmological parlance. The total amount of baryonic matter in the universe was measured precisely by the CMB and by observations of primordial nucleosynthesis. When astronomers added up all the baryons they could account for in visible form, in stars, in galaxies, in hot cluster gas, in neutral hydrogen, they fell short of the predicted total by a significant factor. The resolution, now supported by direct observational evidence, is that a large fraction of the universe's baryons reside in the intergalactic medium, primarily in the warm-hot filaments of the cosmic web. Intergalactic space is not a barren void, but the largest reservoir of ordinary matter in the universe, a diffuse, nearly invisible ocean that dwarfs all the stars and galaxies combined in total mass. Some of the oldest light in the universe passed through intergalactic space. The photons of the cosmic microwave background have been traveling through intergalactic space for nearly 13.8 billion years, since the moment the universe became transparent 380,000 years after the Big Bang. These photons have traversed the entire intergalactic medium, crossing the cosmic dark ages when no stars existed, passing through the epoch of reionization when the first galaxies ionized the surrounding hydrogen, continuing through the billions of years of cosmic web formation, and arriving at our detectors carrying the imprint of every large-scale structure they have passed through. They are the oldest photons that can be observed, older than any star, older than any galaxy, older than any structure in the universe other than the dark matter halos that first clumped together in the early universe. When we observe the cosmic microwave background, we are looking at photons that have crossed the entire observable universe through the most ancient and most extensive medium that exists. Neutrinos stream through intergalactic space in unimaginable numbers. Every second, approximately 330 cosmic background neutrinos pass through every cubic centimeter of space in the universe. A relic sea of neutrinos produced in the early universe, analogous to the cosmic microwave background, but produced even earlier, when the universe was about 1 second old and the temperature was around 10 billion degrees. These cosmic background neutrinos permeate the entire intergalactic medium, along with the high-energy neutrinos produced by astrophysical sources, supernova explosions, active galactic nuclei, gamma-ray bursts. Unlike photons, neutrinos interact only through the weak nuclear force and gravity, allowing them to pass through ordinary matter almost unimpeded. Intergalactic space is therefore pervaded by a sea of neutrinos, a ghost ocean of nearly massless particles that pass through galaxies, planets, and human bodies without interaction, carrying information from the earliest moments of the universe and from the most energetic events in its subsequent history. The void regions of the cosmic web contain their own population of galaxies. Despite being the emptiest regions of the universe by definition, cosmic voids are not completely devoid of galaxies. They contain a population of small, typically blue, star-forming galaxies that are isolated from the larger galaxy structures, the void galaxies. These void galaxies evolve in an environment very different from galaxies in filaments or clusters. They have fewer neighbors to interact with. They are exposed to different radiation fields, and they accrete gas from an environment that is less processed and less metal-enriched than the gas in denser environments. Studies of void galaxies provide a controlled comparison sample for understanding how environment affects galaxy evolution. Since void galaxies are the closest approximation to galaxies evolving in isolation that the universe provides, they tend to be smaller, less massive, bluer, and more gas-rich than typical galaxies, consistent with slower evolution in the absence of the environmental processes that transform galaxies in denser regions. The intergalactic medium contains the building blocks of future galaxies. Not all of the gas in the intergalactic medium has already been processed through a galaxy. A significant fraction of the diffuse gas in the filaments of the cosmic web is relatively pristine, composed primarily of hydrogen and helium with only modest metal enrichment from galactic outflows, and represents raw material that has not yet been incorporated into any galaxy or star. This gas continues to flow along the cosmic web filaments, accreting onto galaxies and fueling their star formation. In the most distant, early universe, this cosmic accretion was the primary fuel for the intense star formation rates observed in early galaxies. Today, with star formation rates across the universe much lower than their peak, the intergalactic medium still supplies gas to galaxies, but more slowly. In the far future, as the reservoir of cold, accretable intergalactic gas is gradually consumed, and as dark energy continues to expand the universe and dilute the remaining gas, this supply will dwindle further, and the already declining rate of star formation across the universe will continue its slow decline toward eventual cessation. The cosmic web connects structures that appear separate. When astronomers look at the large-scale distribution of galaxies, they see what appears to be a collection of separate objects, clusters, groups, and individual galaxies separated by vast distances. But the cosmic web reveals that these apparently separate objects are in fact connected by filaments of dark matter and gas, by the gravitational flows that funnel matter from one region to another, by the shared history of emerging from the same set of primordial density fluctuations. Two galaxy clusters separated by hundreds of millions of light-years may be connected by a filament of dark matter and warm gas that contains no bright galaxies, but that links them gravitationally and physically. The separation between galaxies in intergalactic space is not a disconnection. It is a connection of a different and more subtle kind, mediated by the dark structure underlying the visible universe. Intergalactic space contains echoes of ancient explosions. When a massive star explodes as a supernova, or when a galaxy merger drives enormous outflows of gas from its central regions, the shock waves and energy from these events propagate outward into the intergalactic medium, heating it, compressing it, and creating turbulence that can persist for billions of years. The hot gas in galaxy clusters contains the accumulated energy of billions of years of supernova explosions and AGN outbursts, stored in the thermal energy of the intracluster medium. Radio relic structures in merging clusters are direct echoes of the shock waves from cluster collisions that occurred billions of years ago. The intergalactic medium is not a clean, undisturbed medium. It is an ancient battlefield, carrying in its temperature, density, and composition the signatures of every energetic event that has occurred within it over the history of the universe. Reading those signatures is the work of decades of observations and the subject of thousands of research papers. The Hubble constant measures the expansion rate of intergalactic space. The Hubble constant, the parameter that describes how fast the universe is expanding, is fundamentally a statement about intergalactic space. It tells us how fast the distance between any two objects not bound by gravity is increasing per unit of distance between them. Currently measured at approximately 70 kilometers per second per megaparsec, the Hubble constant means that for every 3.26 million light-years of intergalactic distance, the separation between objects is increasing by about 70 kilometers per second. Two galaxies separated by 3 billion light-years are moving apart at about 70,000 kilometers per second. Two galaxies separated by 14 billion light-years are moving apart at approximately the speed of light, the approximate location of the cosmic horizon, beyond which light can never reach us. The Hubble constant is therefore not merely a number in a cosmological equation, but a physical statement about the rate at which intergalactic space itself is being created between every pair of unbound objects in the universe. Some of the most energetic events in the universe occur in intergalactic space. Gamma-ray bursts, the most energetic electromagnetic events in the known universe, release their energy into intergalactic space in jets of gamma radiation that can be detected across the entire observable universe. The afterglow of a gamma-ray burst, as the jet decelerates by sweeping up intergalactic gas, can be detected for days to weeks after the initial event, providing information about the density of the intergalactic medium along the line of sight. Galaxy cluster mergers release energies of 10 to the power of 64 ergs over their billion-year timescales, more energy than a galaxy emits in light over its entire lifetime, deposited as heat into the intracluster medium and as shock waves propagating through the cluster gas. The jets of radio galaxies carry energy of comparable magnitude into the surrounding intergalactic medium over the active lifetimes of the central AGN. Intergalactic space is not a quiet arena of gentle processes. It is the site of the most energetic events in the universe, events that shape the thermal and kinematic state of matter on the largest scales. The first galaxies formed in the densest regions of the intergalactic medium. The transition from a featureless, nearly uniform early universe to the complex, structured cosmos we observe today began with the collapse of the densest regions of the early dark matter distribution into the first dark matter halos. Gas cooled and condensed within these halos, forming the first stars and galaxies. These first galaxies were small, far smaller than the Milky Way, and they formed preferentially in the densest regions of the dark matter web, at the intersections of the first protofilaments. The intergalactic medium surrounding these first galaxies was neutral hydrogen, the fog of the cosmic dark ages that the ionizing radiation from the first stars and galaxies then began to clear. The first galaxies were therefore simultaneously the products of the intergalactic medium, formed from the gas it contained, and the agents of its transformation, converting it from neutral to ionized, and beginning the process of chemical enrichment with the metals from their first supernovae. Intergalactic space is where the universe keeps most of its history. The intergalactic medium carries chemical, thermal, and kinematic records of every significant event in the history of the universe. Its metal content records the cumulative output of every star that has ever died and expelled its synthesized elements into space. Its temperature records every major energy injection event, reionization, AGN feedback, cluster mergers. Its density distribution records the history of structure formation under dark matter gravity and dark energy acceleration. Its ionization state records the history of the universe's radiation field, from the darkness of the cosmic dark ages through the reionization epoch and the subsequent evolution of the extragalactic radiation background. The intergalactic medium is, in this sense, the most comprehensive archive in the universe, a diffuse, three-dimensional record of cosmic history that spans the entire observable universe and stretches back almost to the beginning of time. Reading that archive, through quasar spectroscopy, X-ray observations, radio surveys, and the next generation of large-scale structure surveys, is the work of contemporary cosmology. The future of intergalactic space will be increasingly isolated. The acceleration of the universe's expansion, driven by dark energy, means that the intergalactic space of the far future will be progressively more isolated than today. Galaxies beyond a certain distance are already receding from us faster than light, carried by the expansion of space beyond our cosmic horizon, never to be seen again. Over the next hundreds of billions of years, as the expansion continues to accelerate, more and more galaxies will cross this horizon and be lost to us forever, their light redshifted beyond detectability. What will remain observable will be only the most nearby galaxies, those bound to us by gravity within the local group, and perhaps a few nearby groups. The intergalactic space of the distant future will be emptier, not because matter has disappeared, but because the expansion has carried it beyond the reach of any signal. An intelligent observer in the far future, in a universe trillions of years old, might see a cosmos that appears to contain only a handful of galaxies, with no evidence of the 2 trillion galaxies that filled the observable universe in our epoch. Intergalactic space is where the universe breathes. There is a cycle that operates on scales that dwarf every other process in the cosmos. Gas from the intergalactic medium flows along filaments into galaxies, where it forms stars and feeds black holes. Stars process that gas, creating heavy elements, and then return it, through winds, supernovae, and planetary nebulae, to the interstellar medium of the galaxy. From there, galactic winds and AGN jets carry it outward, back into the intergalactic medium, where it mixes with the primordial gas, cools, and eventually flows back toward galaxies along filaments. This baryon cycle, the circulation of ordinary matter between the intergalactic medium and galaxies on timescales of billions of years, is the fundamental metabolic process of the universe. It determines the rate at which stars form, the chemical enrichment of the universe over time, the thermodynamic state of the intergalactic medium, and the future of galaxy evolution. The universe breathes, slowly and enormously, on timescales longer than the age of the Earth, through lungs that span millions of light years. The Milky Way is embedded in a larger dark matter halo that extends far into intergalactic space. The visible part of the Milky Way, the disk of stars, the central bulge, the spiral arms, spans about 100,000 light years. But the dark matter halo that surrounds it extends far beyond the visible galaxy, reaching perhaps 300,000 to 600,000 light years from the center in all directions. Within this halo, the boundary between the Milky Way and intergalactic space is not a sharp line, but a gradual transition. The dark matter density decreases smoothly from the concentrated inner halo to the surrounding intergalactic medium. The outer edge of the halo is defined not by any physical boundary, but by the radius at which the Milky Way's gravitational influence equals that of the surrounding large-scale environment. Beyond that radius, material does not orbit the Milky Way. It belongs to the larger gravitational potential of the local group and the structures beyond it. The galaxy we live in extends far further into intergalactic space than the stars suggest. Galaxy groups are the primary environment for galactic cannibalism. The most common outcome for a small galaxy that wanders into a galaxy group is absorption by the group's dominant galaxy, a process called galactic cannibalism that has shaped the growth of large galaxies throughout cosmic history. When a dwarf galaxy falls into the potential well of a much larger galaxy, tidal forces strip its outer stars into tidal streams, while the denser inner regions slowly sink toward the center of the larger galaxy through a process called dynamical friction. Eventually, the remnant merges with the larger galaxy, adding its mass of stars, gas, and dark matter to the growing giant. The Milky Way has undergone this process many times, absorbing dozens of smaller galaxies over its lifetime. The chemical and kinematic signatures of these absorbed companions are preserved in the stellar populations of the Milky Way's halo, where astronomers can reconstruct the history of the galaxy's assembly from the properties of its oldest stars. Radio observations reveal the large-scale magnetic structure of galaxy clusters. The hot gas in galaxy clusters emits synchrotron radiation, radio waves produced by electrons spiraling around magnetic field lines, that reveals the magnetic field structure of the intracluster medium. In some merging clusters, this synchrotron emission is organized into enormous structures, radio halos, which are diffuse sources of radio emission filling the central regions of merging clusters and extending for millions of light years, and radio relics, which are elongated arcs of radio emission at the peripheries of clusters, marking the locations of merger-driven shock waves. The electrons producing this emission are accelerated by the turbulence and shock waves generated in cluster mergers, and the structures they illuminate are among the largest coherent radio-emitting objects in the universe. Observations of these structures with radio telescopes trace the history of mergers and the physics of particle acceleration in the most energetic environments that exist. The universe's large-scale structure is sensitive to the mass of neutrinos. Neutrinos are nearly massless particles that stream freely through the universe, but their small but non-zero mass has a measurable effect on the large-scale structure of the cosmos. Neutrinos travel at close to the speed of light and can escape from dark matter potential wells that would trap ordinary matter, smoothing out small-scale density fluctuations in the early universe. The more massive the neutrinos, the more they suppress the formation of small-scale structure. By measuring the statistical properties of the large-scale structure of galaxies and the cosmic microwave background with high precision, cosmologists can constrain the sum of the masses of the three known neutrino types. Current measurements suggest that the sum of neutrino masses is less than a fraction of an electron volt, extraordinarily small by the standards of particle physics. But even this tiny mass leaves a detectable imprint on the structure of the cosmic web. The architecture of intergalactic space is, in this sense, a particle physics detector. The pattern of galaxies across the sky encodes information about the properties of the lightest known massive particles. The Sloan Great Wall is one of the largest known structures in the observable universe. Among the most striking features revealed by large-scale galaxy surveys is the Sloan Great Wall, a filamentary superstructure of galaxies and galaxy clusters spanning approximately 1.38 billion light-years, identified in the Sloan Digital Sky Survey. At the time of its discovery in 2003, it was the largest known structure in the universe, though subsequent surveys have revealed even larger features. The Sloan Great Wall is not a wall in the strict sense. It is a complex, elongated structure of interconnected filaments and clusters, but it represents an extraordinary concentration of matter along one of the largest dimensions of the observable cosmic web. Its existence is consistent with theoretical predictions of structure formation, but its full extent and internal structure continue to be refined as larger and more detailed surveys map the universe at greater distances. The intergalactic medium can be mapped by its effect on radio signals from pulsars. Radio pulses from pulsars, the rapidly rotating neutron stars that emit beams of radio radiation, are dispersed by the free electrons they encounter as they travel through space, with lower frequency components arriving slightly later than higher frequency ones. By measuring this dispersion, astronomers can estimate the total column density of free electrons along the line of sight to the pulsar. For nearby pulsars within the Milky Way, this technique maps the distribution of free electrons within our galaxy. For extragalactic sources, particularly fast radio bursts, the dispersion measures the total electron content along the entire line of sight through the intergalactic medium. The comparison of observed dispersion measures with predictions from models of the intergalactic medium's electron density provides a direct probe of the ionized gas content of intergalactic space at different redshifts and in different environments, a powerful complement to the quasar absorption line techniques that probe the neutral and weakly ionized gas. Protoclusters are the progenitors of galaxy clusters, seen in the early universe. In the early universe, at redshifts of 2 and beyond, when the universe was less than a quarter of its current age, the galaxy clusters we see in the local universe had not yet fully assembled. What existed in their place were protoclusters, overdense regions of the universe containing many more galaxies than the average surrounding field, but not yet collapsed into the gravitationally bound, hot gas-filled clusters of the present day. Protoclusters are identified in galaxy surveys as extended overdensities of galaxies across projected areas of tens of millions of light-years, often containing vigorous star formation in their member galaxies, activity that will later be quenched as the protocluster collapses and the intracluster medium heats up. Studying protoclusters provides a direct window into the formation of the most massive structures in the universe, observing the process of cluster assembly at the moment it is occurring rather than after it has been completed. The void fraction of the universe has increased over cosmic time. In the early universe, when matter was more uniformly distributed, the fraction of the universe's volume occupied by voids was smaller. The density contrasts between overdense and underdense regions were still developing under gravity. Over the billions of years since, gravity has amplified these contrasts. Matter has flowed from underdense regions toward overdense ones, making the overdense regions denser and the underdense regions emptier. As a result, the fraction of the universe's volume that is classified as void has grown over cosmic time, and the voids themselves have grown in size as they have emptied and expanded. This evolution of the void population with cosmic time is a measurable signature of the growth of structure under gravity and dark energy, and it provides constraints on cosmological parameters, including the dark energy equation of state. The expansion of voids over cosmic time is one of the clearest manifestations of the universe's ongoing structural evolution. Some intergalactic filaments have been directly imaged for the first time. For most of the history of observational cosmology, the filaments of the cosmic web were detected statistically through the clustering of galaxies, rather than directly imaged as coherent structures. The diffuse gas in the filaments is too faint to image directly with most techniques. In recent years, however, advances in instrumentation and observational strategy have allowed direct imaging of individual filaments. The Subaru telescope, using its wide-field camera and long exposure times, has detected the fluorescent emission of hydrogen gas in filaments surrounding massive galaxy clusters at high redshift, illuminated by the ultraviolet radiation of the quasars embedded within them. The resulting images show, for the first time, the actual spatial structure of cosmic web filaments, not inferred from galaxy positions, but directly seen as extended structures of glowing gas in the spaces between galaxies. These direct detections confirm the predictions of cosmological simulations and open a new window into the physical properties of the filaments that connect the universe's nodes. The age of the universe can be measured from the properties of intergalactic space. The Hubble constant, the current expansion rate of the universe, combined with the measured composition of the universe in dark matter, dark energy, and ordinary matter, determines the age of the universe. But the measurement of the Hubble constant itself depends on observations made across intergalactic space, the distances and recession speeds of galaxies, the properties of the cosmic microwave background, and the luminosity distances to type Ia supernovae in distant galaxies. A persistent tension between the Hubble constant measured from the early universe, via the CMB, and the value measured from the local universe, via supernovae and the distance ladder, is one of the most significant unresolved discrepancies in modern cosmology. The two methods give values that differ by a few percent, but with high statistical significance, suggesting either systematic errors in one or both measurements or the presence of new physics, perhaps a new component of the universe's energy budget, a time-varying dark energy, or an early dark energy episode that modified the universe's expansion history. The resolution of this tension may require not just new observations, but a revision of our cosmological model. The intergalactic medium contains antimatter in negligible quantities. The early universe produced matter and antimatter in nearly equal amounts during the Big Bang, but a slight asymmetry, one extra matter particle for every billion matter and antimatter pairs, left the universe with the matter-dominated content we observe today. The matter and antimatter annihilated each other almost completely, releasing the photons that make up the cosmic microwave background, while the surviving matter formed everything we observe. In the intergalactic medium today, antimatter is present in only trace quantities, cosmic ray positrons and antiprotons, produced by the interactions of high-energy cosmic rays with interstellar gas, and potentially a small flux from the annihilation of dark matter particles if dark matter is its own antiparticle. The intergalactic medium is overwhelmingly composed of ordinary matter, and the question of why why the matter-antimatter asymmetry existed and what produced it, remains one of the most profound unsolved problems in physics. Galaxy evolution and intergalactic environment are inseparable. For much of the 20th century, galaxies were studied largely as isolated objects, their properties determined primarily by their initial conditions, their mass, spin, and composition at formation. The picture that has emerged from decades of observations is very different. The properties of a galaxy are strongly shaped by the environment it inhabits. Galaxies in dense cluster environments are typically redder, older, and gas-poor compared to galaxies in field or void environments. The mechanisms responsible, ram pressure stripping, harassment by other cluster galaxies, strangulation of the gas supply by the hot intracluster medium, and tidal interactions, all operate through the intergalactic medium and the gravitational environment of the cluster. The properties of any individual galaxy cannot be fully understood without understanding the intergalactic environment it has inhabited throughout its history. The medium between galaxies is not a passive backdrop for galaxy evolution. It is one of its primary drivers. Intergalactic space hosts some of the universe's most powerful accelerators. The shock waves produced by galaxy cluster mergers, by the jets of active galactic nuclei, and by the accretion of gas onto galaxy clusters are capable of accelerating charged particles to energies far exceeding anything achievable in the most powerful human-built particle accelerators. The electrons accelerated in cluster merger shock waves produce the radio relics observed in merging systems. The protons accelerated by the same shocks may be responsible for some of the highest energy cosmic rays detected at Earth. The intergalactic medium is permeated by cosmic rays, protons, electrons, and heavier nuclei at a wide range of energies, all having been accelerated by the energetic processes operating in the intergalactic environment. Understanding the acceleration mechanisms, the propagation of these particles through the intergalactic magnetic field, and their eventual energy losses through interactions with the cosmic microwave background is central to the field of high-energy astrophysics and to understanding the energy budget of the intergalactic medium. The Milky Way is losing gas to the intergalactic medium. The Milky Way is not a closed system. Gas escapes from the galaxy continuously, blown out by the collective energy of supernovae, pushed by radiation pressure from massive stars, and driven by the outflows of the central region. Some of this gas falls back into the galaxy after cooling in the halo, in a process called the galactic fountain, but some escapes entirely, joining the intergalactic medium. Observations of the Milky Way's halo have detected high-velocity clouds of gas, moving at speeds inconsistent with ordinary galactic rotation, that may represent either infalling intergalactic gas or outflowing galactic material caught in the act of escaping. The Magellanic Stream, the enormous ribbon of gas trailing from the Magellanic Clouds, is itself partially composed of gas stripped from the satellite galaxies and being incorporated into the Milky Way's circumgalactic medium. The Milky Way is continuously exchanging material with its intergalactic environment, inhaling gas along filaments and exhaling processed material into the halo and beyond. The epoch of peak star formation was also the epoch of peak intergalactic activity, at a redshift of approximately 2 to 3, when the universe was roughly 2 to 4 billion years old. The rate of star formation across all galaxies combined reached its highest level in cosmic history, roughly 10 times the current rate. This epoch, sometimes called cosmic noon, was also the period of peak AGN activity, the highest density of luminous quasars in the universe's history, injecting enormous amounts of energy into the intergalactic medium. The simultaneous peak of star formation and black hole accretion activity at this epoch is thought to reflect the efficient delivery of cold gas from the cosmic web to galaxies, a period when the cosmic plumbing was at its most productive, channeling pristine intergalactic gas along filaments and into the hungry star-forming cores of young galaxies. The intergalactic medium was the most active it has ever been during cosmic noon, and understanding what changed to bring this epoch to an end, why star formation rates declined so dramatically after redshift 2, is one of the central questions of galaxy evolution research. The Sunyaev-Zel'dovich effect has been used to find clusters billions of light-years away. The South Pole Telescope and the Atacama Cosmology Telescope have used the Sunyaev-Zel'dovich effect, the distortion of the cosmic microwave background by hot cluster gas, to conduct all-sky surveys for galaxy clusters across cosmic time, finding thousands of clusters at distances ranging from nearby to more than 10 billion light-years. Because the Sunyaev-Zel'dovich signal does not fade with distance the way ordinary brightness does, this technique is uniquely powerful for finding the most massive clusters at the highest redshifts, the clusters that formed earliest and that trace the most extreme peaks of the primordial density field. The distribution of these high redshift clusters, their numbers, masses, and clustering, provides strong constraints on cosmological parameters, particularly the amplitude of primordial density fluctuations and the sum of neutrino masses. The hot gas filling the intergalactic space within these distant clusters has been used as a cosmological tool, encoding in its thermal properties information about the early universe and the growth of structure across billions of years. The transition from intergalactic to circumgalactic medium is gradual and complex. The intergalactic medium does not end abruptly at the edge of a galaxy and give way cleanly to the galaxy's interstellar medium. Between the two is the circumgalactic medium, a complex, multi-phase region of gas that surrounds galaxies out to distances of hundreds of thousands of light-years, serving as both a reservoir for future star formation and a sink for gas expelled from the galaxy's disk. The circumgalactic medium contains gas at a wide range of temperatures and densities, cold, dense clouds that may be condensing to feed future star formation, warm, ionized gas characteristic of the interface between outflowing galactic gas and infalling intergalactic gas, and hot dilute gas heated by supernova-driven winds. The circumgalactic medium is the galaxy's atmosphere, its interface with the intergalactic environment, and its properties determine how efficiently the galaxy can accrete new material and how far galactic outflows can travel before mixing back into the intergalactic medium. It is one of the most active areas of current observational and theoretical research in galaxy evolution. The long-term fate of intergalactic space is determined by dark energy. The intergalactic space of the far future will be profoundly different from what it is today. As dark energy continues to accelerate the expansion of the universe, the intergalactic distances between galaxy clusters will grow exponentially. The gas in the intergalactic medium will be diluted to even lower densities than it already has. The cosmic microwave background will be redshifted to longer and longer wavelengths, its temperature dropping below a degree Kelvin and eventually approaching absolute zero. The large-scale structure of the cosmic web, the filaments and clusters and voids, will gradually dissolve as dark energy pulls the components apart faster than gravity can hold them together. The cosmic web is a feature of this particular epoch in the universe's history, a transient arrangement of matter shaped by the interplay of gravity and dark energy at a specific moment in cosmic time. In the deep future, the universe will be composed not of a web of connected structure, but of isolated gravitational islands, remnant galaxy groups and clusters, separated by an ever-expanding, ever-emptier intergalactic void. The universe contains structures so large they challenge the cosmological principle. The cosmological principle, the foundational assumption of modern cosmology that the universe is homogeneous and isotropic on sufficiently large scales, meaning it looks the same from every point and in every direction, is one of the pillars of the standard cosmological model. It predicts that on scales larger than about 300 million light-years, the universe should be essentially uniform, with no preferred directions and no structures larger than what statistical fluctuations allow. Several observed structures appear to strain this principle. The Hercules Corona Borealis Great Wall, a putative superstructure of galaxies spanning more than 10 billion light-years, exceeds the scale at which the cosmological principle requires homogeneity. Whether this structure is a real coherent entity or a statistical artifact of the surveys used to detect it remains actively debated. The cosmological principle has survived every serious challenge so far, but the discovery of structures that genuinely violated it would require a fundamental revision of our understanding of the universe's large-scale architecture. Galaxy cluster observations have confirmed that dark energy is real. One of the most powerful independent lines of evidence for dark energy comes from the study of galaxy clusters across cosmic time. If the universe's expansion is accelerating, as dark energy requires, then the growth of large-scale structure should be suppressed compared to a universe without dark energy, because the accelerating expansion works against the gravitational clumping that builds clusters. By counting galaxy clusters at different redshifts and comparing the cluster mass function, the number of clusters per unit volume as a function of mass, at different epochs, astronomers can directly test whether the growth of structure has been suppressed in the way dark energy predicts. The observed cluster counts, combined with measurements of individual cluster masses through gravitational lensing and X-ray observations, are consistent with a universe dominated by dark energy with the properties inferred from CMB and supernova observations. The same dark energy that drives the expansion of intergalactic space also suppresses the formation of the structures embedded within it. Some galaxy clusters contain fossil groups at their centers. In the centers of some galaxy clusters, astronomers have found what are called fossil groups, systems in which nearly all the luminous mass of what was once a galaxy group has merged into a single enormous elliptical galaxy, leaving behind a mostly empty cluster environment dominated by hot gas and dark matter. Fossil groups are thought to represent the endpoint of efficient galactic cannibalism, groups in which the dynamical processes that drive galaxy mergers operated so efficiently that the group's dominant galaxy consumed all its major companions before additional infall of galaxies could replenish the population. They are the tombstones of galaxy groups, regions of the intergalactic medium that once contained multiple bright galaxies, all of which have been absorbed into a single dominant system, their stars now part of the largest galaxies in the universe. The intergalactic medium scatters and absorbs high-energy radiation. Not all radiation travels freely through intergalactic space. Very high-energy gamma rays, photons with energies above a few hundred billion electron volts, are absorbed by the extragalactic background light, the diffuse sea of infrared, optical, and ultraviolet photons emitted by all the stars and galaxies in the history of the universe, filling all of intergalactic space. When a very high-energy gamma ray encounters one of these background photons, the two can annihilate and produce an electron-positron pair, a process that effectively makes the universe opaque to gamma rays above a certain energy at a certain distance. This gamma-ray horizon limits the distance from which the most energetic gamma rays from blazars and gamma-ray bursts can reach Earth, and its measurement provides information about the total energy content of the extragalactic background light, a cumulative record of all the starlight ever produced in the observable universe. The circumgalactic medium is being mapped by a new generation of spectrographs. The circumgalactic medium, the extended gaseous halo surrounding galaxies out to hundreds of thousands of light years, is one of the most active areas of current observational research in extragalactic astronomy. New and planned instruments, including the WEAVE spectrograph at the William Herschel Telescope and the foremost survey facility at the Vista Telescope, are designed to survey the circumgalactic medium around thousands of galaxies simultaneously, using the absorption signatures the gas leaves in the spectra of background quasars. The circumgalactic medium provides a record of a galaxy's entire history of gas exchange with its environment, the inflows that fed star formation and the outflows that expelled processed gas back into intergalactic space. Mapping it comprehensively will provide the most complete picture yet of how galaxies exchange material with their environments across cosmic time. The topology of the cosmic web can be quantified mathematically. The cosmic web is not just qualitatively complex. It has a quantifiable topological structure that can be measured using mathematical tools borrowed from topology, the branch of mathematics concerned with the properties of spaces that are preserved under continuous deformations. Astronomers apply techniques such as the Euler characteristic, Minkowski functionals, and persistent homology to galaxy survey data to quantify the number, size, and connectivity of the filaments, walls, voids, and clusters that make up the cosmic web. These topological measures provide constraints on cosmological parameters, particularly the amplitude of density fluctuations and the dark energy equation of state, that are complementary to the power spectrum and correlation function measures traditionally used in large-scale structure analysis. The cosmic web has a precise mathematical fingerprint that encodes information about the physics that created it, and modern cosmology is developing the tools to read that fingerprint with increasing precision. Intergalactic absorption lines reveal the chemical evolution of the universe. When astronomers observe quasar spectra at different redshifts, different distances, and therefore different epochs in cosmic history, the absorption lines produced by intergalactic gas reveal how the chemical composition of that gas has changed over time. At high redshift, in the earliest observable epochs, the intergalactic medium shows very low metal abundances, barely any elements heavier than hydrogen and helium, consistent with gas that has had very little contact with stellar nucleosynthesis products. At lower redshifts, the metal content of the intergalactic medium has increased substantially, reflecting the cumulative output of billions of years of supernovae and AGN-driven outflows distributing heavy elements from galaxies into the surrounding medium. This chemical enrichment history, read from absorption lines in quasar spectra, provides a direct observational record of how the intergalactic medium has been progressively polluted by the products of stellar evolution, a record that traces the history of star formation and feedback across the entire observable universe. The local void is a vast emptiness that borders the local group. Immediately adjacent to the local group, the galaxy group that contains the Milky Way, lies the local void, a region of substantially below average galaxy density that extends for roughly 150 million light-years. The local void is one of the reasons why the local group appears to be moving with an unusually high velocity relative to the cosmic microwave background reference frame. In addition to the pull of the Great Attractor and other overdense structures ahead of us, We are being pushed outward from the local void behind us by the slight excess of matter in the surrounding regions relative to the void itself. This void repulsion, the kinematic consequence of an underdense region pushing the surrounding matter outward as it expands faster than the cosmic average, contributes to the peculiar velocity of the local group and illustrates how even empty space exerts an influence on the motion of galaxies through the differential pressure of the surrounding cosmic structure. Gravitational waves from merging black holes travel through intergalactic space. The gravitational waves detected by LIGO and Virgo since 2015, produced by merging black holes and neutron stars, travel through intergalactic space to reach Earth. Unlike electromagnetic radiation, gravitational waves are not absorbed, scattered, or significantly affected by the matter they pass through on their journey. They travel at the speed of light and arrive at Earth with their amplitude and phase encoding information about their source that has been preserved essentially unchanged across the billions of years and billions of light years of their journey. As the sensitivity of gravitational wave detectors improves, and as space-based detectors like LISA come online, gravitational waves from merging supermassive black holes in distant galaxy mergers will become detectable, sources that release energies equivalent to millions of solar masses in gravitational wave emission over timescales of years. These signals will probe the population of supermassive black holes and galaxies across cosmic time, providing a gravitational wave counterpart to the electromagnetic surveys that have mapped the universe's large-scale structure. The universe contains a diffuse background of X-ray radiation from intergalactic space. The entire sky glows faintly in X-rays, not from individual discrete sources, but from a diffuse, nearly isotropic background that originates partly within our galaxy, but is dominated, at higher energies, by the summed emission of millions of active galactic nuclei distributed across the observable universe. This cosmic X-ray background was discovered in the early 1960s and was for decades one of the great mysteries of X-ray astronomy. Where was it coming from? Large area surveys with X-ray satellites resolved the question by showing that the background is largely composed of the unresolved emission of millions of distant AGN, quasars, and Seyfert galaxies, distributed across the universe. The diffuse background that remained after all individually detectable sources were removed comes partly from truly diffuse hot gas in the intergalactic medium of galaxy clusters and filaments, glowing in X-rays with a temperature reflecting the thermodynamic history of the structure formation process. The sky in X-rays is a map of the hot universe, the intergalactic gas heated by gravitational collapse and AGN feedback across billions of years. The detection of the cosmic web in emission is one of astronomy's grand challenges. For decades, the cosmic web has been mapped primarily through the positions of galaxies, the bright nodes and filaments visible in galaxy surveys, and through absorption features in quasar spectra that reveal the gas between the galaxies. The direct detection of the filaments in emission, seeing the glow of the gas itself rather than inferring its presence from absorption, has been one of the most challenging goals of observational cosmology. The gas in filaments is too diffuse and too faint to detect with most instruments. Recent advances with integral field spectrographs on large telescopes have enabled the detection of emission from filaments around high redshift quasars, where the quasar's radiation fluorescently excites the surrounding gas, making it glow in the Lyman alpha line of hydrogen. The next generation of extremely large telescopes and wide-field spectrographs promises to extend this capability to lower redshifts and to filaments that are not illuminated by a nearby quasar, opening the full extent of the cosmic web to direct observation for the first time. The cosmic web has been reproduced in laboratory experiments. The structure of the cosmic web, the network of filaments, nodes, and voids produced by gravitational collapse of matter under the influence of dark matter, has a remarkable resemblance to certain structures produced in completely different physical contexts. The distribution of neurons in the human brain, the growth pattern of slime molds, the architecture of electrical discharge networks. These resemblances are not merely aesthetic. They reflect a common underlying mathematics of network formation under local connection rules and growth processes, despite the profoundly different physical mechanisms involved. Scientists have used these connections to develop new algorithms for mapping the cosmic web based on principles borrowed from the study of biological networks, and conversely, cosmological simulations have been used to inspire models of neural and vascular network formation. The cosmic web is not just an object of astronomical study. It is a window into the universal mathematics of network formation. Intergalactic gas clouds can be detected through their shadow on the cosmic microwave background. Just as the hot intracluster medium produces a distortion in the cosmic microwave background through the Sunyaev-Zeldovich effect, any gas along the line of sight to the CMB can in principle affect the photons passing through it. Cold gas clouds, dense enough and with the right composition, can absorb specific wavelengths of CMB photons, creating a shadow in the CMB at those wavelengths. This effect has been used to detect molecular clouds within our own galaxy. In principle, sufficiently dense intergalactic gas clouds could produce detectable signatures in CMB observations, a new technique for mapping the cold component of the intergalactic medium that complements the X-ray and ultraviolet methods used to study its warmer phases. As CMB observatories achieve ever finer angular resolution and sensitivity, the range of intergalactic phenomena detectable through their influence on the cosmic microwave background continues to expand. Protoclusters in the early universe experienced the most intense star formation ever. In the protoclusters of the high redshift universe, the overdense regions that would eventually collapse into the galaxy clusters we see today, star formation rates reached values orders of magnitude higher than anything observed in the local universe. Submillimeter galaxies, detected by their thermal dust emission at submillimeter wavelengths, represent some of the most intensely star-forming systems ever found, forming stars at rates of hundreds to thousands of solar masses per year in concentrated bursts fueled by the efficient delivery of cold gas from the surrounding cosmic web. Many of these extreme star-forming systems are found in overdense environments consistent with protoclusters, suggesting that the densest nodes of the early cosmic web were also the sites of the most spectacular star formation ever to occur. The intergalactic environment of these protoclusters, saturated with the ultraviolet radiation of millions of young massive stars, enriched with metals from the supernovae of the earliest stellar generations, and threaded by the outflows from the first active galactic nuclei, was an environment of extraordinary and violent productivity that has no equivalent in the universe today. The missing satellites problem involves the intergalactic neighborhood of the Milky Way. One of the long-standing tensions between cosmological predictions and observations concerns the predicted and observed numbers of satellite galaxies around the Milky Way. Simulations of structure formation in a universe dominated by cold dark matter predict that large galaxies like the Milky Way should be surrounded by hundreds or thousands of small dark matter subhalos, each potentially hosting a dwarf galaxy. Observations have revealed only dozens of satellite galaxies around the Milky Way. This discrepancy, the missing satellites problem, has several proposed resolutions. The smallest dark matter halos may be too small to accumulate enough gas to form stars. The ultraviolet radiation from the epoch of reionization may have evaporated the gas from small halos, or supernovae feedback may have expelled gas from small galaxies before it could form many stars. The resolution may involve a combination of all these effects. The intergalactic neighborhood of the Milky Way, the local group and its surroundings, serves as a laboratory for testing cosmological predictions about small-scale structure formation in ways that are impossible to study in more distant environments. The epoch of reionization transformed the intergalactic medium irreversibly. The reionization of the intergalactic medium, the transformation of its hydrogen from neutral to ionized by the first generations of stars and galaxies, was not a gentle process. The ultraviolet photons from the first luminous sources ionized the surrounding gas and heated it rapidly from temperatures of a few tens of degrees above absolute zero to tens of thousands of degrees. This heating had immediate and lasting consequences for the formation of small galaxies. The sudden increase in gas temperature raised the gene's mass, the minimum mass of a gas cloud that can collapse under gravity, dramatically suppressing the formation of low-mass galaxies throughout the intergalactic medium. Small dark matter halos that had been accumulating gas suddenly found their gas too hot to collapse into stars, effectively sterilizing them. Reionization therefore not only ionized the intergalactic medium, it altered the subsequent trajectory of galaxy formation, suppressing small-scale structure formation in a way whose effects persist to this day in the relative scarcity of small galaxies compared to the predictions of dark matter models without this feedback. The James Webb Space Telescope is observing the intergalactic medium at the edge of time. Among the most ambitious science programs of the James Webb Space Telescope is the characterization of the intergalactic medium during and immediately after the epoch of reionization, the period from about 400 million to 1 billion years after the Big Bang, when the universe transitioned from neutral to ionized. Webb's infrared sensitivity allows it to detect the spectra of galaxies and quasars at redshifts greater than 6, when the universe was less than 1 billion years old, and to analyze the absorption features produced by the intergalactic hydrogen along the line of sight. Quasars at very high redshifts show a Gunn-Peterson trough, a near-total absorption of the quasar's ultraviolet emission by neutral hydrogen in the intergalactic medium, which had not yet been completely ionized when the quasar's light was emitted. By comparing the spectra of quasars at different high redshifts, Webb is mapping the progress of reionization across time, determining when different regions of the universe became transparent and tracing the spread of ionized bubbles from the first luminous sources outward through the neutral intergalactic medium of the early universe. The Hubble Ultra Deep Field revealed the depth of intergalactic space. In 2003 and 2004, the Hubble Space Telescope pointed at an apparently blank patch of sky in the constellation Fornax, a region containing no bright foreground stars or galaxies, and exposed it for nearly 1 million seconds over many separate observations. The resulting image, the Hubble Ultra Deep Field, revealed approximately 10,000 galaxies in a patch of sky smaller than 1/10 of the diameter of the full moon. Most of these galaxies are billions of light years away, their light having traveled through the intergalactic medium for billions of years before reaching Hubble's detectors. The image is a coarse sample through the history of the universe. The nearest galaxies are relatively large and well-formed, the more distant ones progressively smaller and less regular, reflecting the earlier state of galaxy assembly in the young universe. What appears as blank darkness to the unaided eye contains, when examined with sufficient sensitivity, a field of galaxies stretching to the edge of the observable universe. A demonstration that the intergalactic space in every direction is not empty, but filled with the light of billions of galaxies too faint to see without extraordinary effort. Intergalactic space is growing in volume every second. The expansion of the universe is not merely a historical fact about the past. It is happening right now, continuously. Every second, the volume of the observable universe increases as space expands. The intergalactic distances between unbound galaxies grow slightly larger with each passing moment. A pair of galaxies separated by 100 million light-years today will, in a billion years, be separated by somewhat more, the difference accumulating imperceptibly moment by moment, driven by the energy of dark energy permeating all of space. This expansion is not like the expansion of a gas into a container. There is no container, no center of expansion, and no edge. Every point in intergalactic space is receding from every other point simultaneously, in a process that has been running since the first fractions of a second after the Big Bang, and that, as far as we can tell, has no foreseeable end. The intergalactic medium contains the record of every supernova that has ever occurred. Every time a massive star has exploded as a supernova anywhere in the universe, the heavy elements it synthesized and expelled have, over billions of years, made their way through the interstellar medium of its host galaxy and eventually, through galactic winds and outflows, into the intergalactic medium. The cumulative chemical composition of the intergalactic medium, its content of carbon, oxygen, magnesium, silicon, iron, and the other products of stellar nucleosynthesis, represents the integrated output of every supernova that has ever occurred, mixed and diluted across the entire volume of intergalactic space. When astronomers measure the metal abundance of intergalactic gas through quasar absorption line studies, they are measuring, in a very real sense, the total productive output of every massive star that has ever lived and died in the observable universe. A chemical census of cosmic history encoded in the composition of the space between galaxies. The future of cosmological observation lies in mapping intergalactic space. The next generation of cosmological surveys, including the Dark Energy Spectroscopic Instrument, the Vera Rubin Observatory's Legacy Survey of Space and Time, and the Euclid Space Mission, are designed to map the positions and distances of hundreds of millions to billions of galaxies across the observable universe, creating the most detailed three-dimensional maps of the large-scale structure ever assembled. These maps will measure the baryon acoustic oscillation scale, the characteristic distance between galaxy overdensities imprinted by sound waves in the early universe, at many different epochs, providing precise measurements of the expansion history of the universe and the properties of dark energy. They will probe the growth of structure through weak gravitational lensing surveys that map the distribution of dark matter across billions of light-years. They will identify thousands of galaxy clusters and map the evolution of cluster properties across cosmic time. The future of cosmology is written in the properties of intergalactic space, in the distances between galaxies, the clustering of matter, and the subtle distortions of background galaxy shapes by the gravitational fields of dark matter along the line of sight. We are immersed in intergalactic space even as we study it. This is perhaps the most important perspective shift that the study of intergalactic space offers. We are not external observers looking at the space between galaxies from a safe distance. We are inside it. The Milky Way is a node in the cosmic web, surrounded by the intergalactic medium on all sides, embedded in the local group, falling toward the great attractor, subject to the same expansion of space that stretches the distances between all unbound objects. The cosmic microwave background that astronomers detect with their instruments is not a distant phenomenon. It surrounds us completely, the oldest light in the universe arriving from all directions simultaneously. The neutrinos from the early universe stream through our bodies at this moment. The dark matter that forms the scaffold of the cosmic web extends through and around us. We are not looking at the universe from outside. We are a small, temporary, luminous arrangement of matter embedded in the middle of something vast, ancient, and extraordinary, studying the medium we are immersed in, with instruments made of its atoms, from a world made of its elements, lit by a star that formed from its gas. And so we return now, slowly, gently, from the spaces between galaxies, from the warm hot filaments and the ancient voids, from the dark matter scaffolding and the rivers of intergalactic gas, from the echoes of billion-year-old collisions and the neutrino ocean and the magnetic threads that stitch it all together. What we found there was not nothing. It was a medium of extraordinary complexity and history, carrying in its temperature and its chemistry and its motion the record of everything the universe has done since the first light ignited in the early dark. It was the scaffolding on which galaxies are built, the reservoir from which they drink, and the ocean into which they exhale. It is the space between everything. And it turns out that the space between everything is one of the most important things in the universe. You have traveled farther tonight than any human spacecraft has ever gone. You drifted through the warm hot gas of cosmic filaments, past the shock waves of merging clusters, through the vast quiet of a void where bright galaxies are simply absent across hundreds of millions of light years. You glimpsed the stars drifting alone in intergalactic space, far from any galaxy, and the ancient photons still crossing the cosmos from the moment it first became transparent. All of this exists, not in a story, not in an equation, but out there, right now, while you rest. Let your breath slow. Let the distances settle into their proper perspective, which is to say, let them become vast enough that they lose their urgency. Nothing that needs your attention is as far away as what you visited tonight. Everything close enough to matter is right here, breathing the same air, under the same sky, circling the same quiet sun. The cosmic web will keep assembling its structures in the dark. The filaments will keep drawing gas toward the clusters. The voids will keep expanding in their slow, patient way, and the light from it all will keep crossing the intergalactic medium, carrying its record of what the universe has done for anyone patient enough to read it. Consider subscribing to Somniora Mind. You're already the kind of person this channel was made for, one quiet mind at a time. Let the last filament fade behind your eyes. Rest now. You've earned it. Good night.